So anyway, my name is Rob French. I work at the SETI Institute in Mountain View, California, which is down the street. I'm sure many of you have heard of it previously. I know you've had previous talks on things like SOFIA and things like that. Dick Simpson is on the call this evening. I believe he's a new association member, and he's one of my coworkers who has been doing radio astronomy work of the kinds that I'll be talking about for a very, very long time. So if you ask really hard questions, I may actually just turn it over to him to answer the questions for you. So we all know that radio is used for communication. Obviously, we do that all the time, and that it's used for communication to spacecraft. But radio waves are used for a lot of other things as well. And so tonight, I would like to talk about some of the ways that radio technology is used to do planetary exploration other than communicating with spacecraft. It's a huge subject, so I'm only going to be talking about 4 specific ways in which radio is used. And I'm going to talk about some very specific discoveries. Obviously, there are many more discoveries that have been made, but I'm going to concentrate on some of the discoveries that have been made more recently, sometimes as recently just as last month, to give it a little bit of a timely feel. But first, I wanted to give just a little bit of an overview of the SETI Institute. I have too many keyboards here, hang on. There we go. Give just a little bit of a brief overview of the SETI Institute, which is at the corner of Central and Bernardo in Mountain View. We're a nonprofit research institute. We've been around since 1984, originally a spinoff from NASA Ames as a home for the NASA SETI group doing sort of classical SETI research, searching for little green men by radio signals. But since then, we've blossomed into a much more generic planetary research organization. We've administered over $250 million in research grants. Most of those were from NASA. We currently have over 160 active grants, $22 million a year budget, and we employ 92 research scientists who together have published nearly 1,000 peer-reviewed publications in 115 distinct journals just in the last 5 years. So we have a very prolific and very productive scientific staff. We hold the NASA contract for planetary protection, which means not only protecting other planets from Earth-based microbes, but protecting Earth from contamination from alien microbes. We have our own radio telescope, which is up in Lassen National Park in Northern California, called the Allen Telescope Array. It was partially funded by Paul Allen, co-founder of Microsoft, hence the name. As of last fall, if you're familiar with GNU Radio, the SDR open source project, we are now the administrator of that project, and we take care of all their grants and all of their organization structure. We have our own radio show called Big Picture Science, which is available on various local radio channels, as well as whatever your favorite podcast source is. All right, so the briefest introduction to the solar system in the world. It's like this, not actual size. However, the planets actually are sort of to actual size. It's just the distances between them are not. Obviously, we have the, can you see my mouse, by the way, if I move it around on the screen?
Yes, we can.
Okay, so we have the 8 classic planets. We have Pluto, which who knows what it is these days, the asteroid belt between Mars and Jupiter, and the Kuiper belt outside of Neptune. Like I said, these are mostly to actual scale in terms of the size of the planets, but how big is the actual solar system itself? And I thought since we were talking about radio, I would talk about this in terms of light travel time. So this is the one-way light travel time sort of on average between the Earth and various bodies. So we have about 1.5 seconds to the moon. So you get, 2.5, 3 seconds round trip for Earth, moon, Earth signals. We have about 8 minutes to the sun, 10 minutes to Mars on average. And then we start getting pretty big. So 40 minutes to Jupiter, almost an hour and a half to Saturn, 2.5 to Uranus, 4 hours to Neptune, and a whopping 5.5 hours to Pluto. So when New Horizons was flying by Pluto, if you wanted to send a signal to the spacecraft, it would take 11 hours round trip time for that signal to get a response back here on Earth. Since the flyby only took about a day, there was really no way to do any sort of real-time communication during that flyby, and it was entirely robotically programmed. The other thing I wanted to talk about in terms of scale, since we are going to be talking a lot about my personal passion in the solar system, which is Saturn and its rings, is the scale of Saturn's rings. So Earth has a diameter roughly 8,000 miles. Saturn's rings are about 175,000 miles in diameter, but at the same time, they're only about 30 feet thick, which is about the height of the house that I'm sitting in right now. So if you were to scale a piece of paper up to the size of the rings, they are actually thinner than a piece of paper at that scale. All right, so moving directly along to our first radio topic here. I want to talk about something that is actually accessible to any ham. And in fact, it may have gotten in the way of you doing HF communication and you didn't even realize it. So we're going to talk about two main bodies here. The first one is Jupiter. Jupiter, of course, is the most massive planet in our solar system. And this is a artist's model of what the interior of Jupiter might look like. What we see on the outside is just a gaseous layer that consists mainly of molecular hydrogen, helium. And then as you go further down in, the pressure and the temperature starts to really, really build up. So we get supercritical hydrogen and helium, which are basically a cross between a liquid and a gas. Then we have liquid metallic hydrogen and helium, which are almost impossible to produce even here on Earth. And then we have a rocky ice or metal core. And at that core, the prediction is that the temperature is around 24,000 Celsius, and it has a pressure of 50 to 100 million atmospheres. So very, very dense core. Now, Jupiter has 4 main moons that orbit around it. These are called the Galilean moons. They were discovered by Galileo in 1610 with his earliest telescope. And they are Io, Europa, Ganymede, and Callisto. And Io is the most interesting of these 4, I think, although people would have their own opinions on that, in that it is the most volcanically active body in the entire solar system. It has over 400 active volcanoes on it. And the reason is that Jupiter has a very strong gravitational field that raises tides. So as the moon goes around the Earth, we all know that the moon raises tides on the Earth. It pulls water into a non-spherical shape so that it flows in and out of your coastlines. You may not realize that the solid Earth beneath your feet is also affected by the moon's gravity, and where you're standing goes up and down by somewhere between 6 and 12 inches a day as the Earth rotates and the moon changes its position relative to where you're standing. Jupiter, on the other hand, has a gravitational tide pull on Io that is 20,000 times stronger. And the tidal bulge that it raises on Io can be up to 300 feet tall. So if you think about what happens with Io as it orbits around Jupiter, and Jupiter is raising this tidal bulge, which moves around the moon, basically it's like you have one of those stress balls and you're squeezing it into different shapes. And as you squeeze it a lot, what happens is you get a lot of friction on the inside, and that friction produces heat. And that heat is what melts the interior and allows this active volcanic activity. The amount of friction that's generated is equivalent to about 10 to the 14th watts. It's 100 terawatts that is being emitted from Io simply due to the friction due to these tides. So these volcanoes emit sulfur, sulfur dioxide, among a lot of other things. And Io, as a result, actually has a tenuous atmosphere that are all of these ions that are being released from these volcanoes. So Jupiter is, I hear somebody in the background. So Jupiter itself has a very strong magnetic field. Just like Earth, it has a magnetic field that's caused by currents that are circulating in its interior level, although in this case, it's probably inside of the metallic hydrogen layer. But the magnetic field is 10 times stronger than that of Earth. And it rotates around the planet at the rate of the rotation of that inner core. But that's not the same rate that Io orbits around the planet. So Jupiter spins on its own axis a lot faster than Io orbits around. So you can think of it as this magnetic field is basically sweeping past Io. And Io has all of these charged particles, all these ions in its atmosphere. So this magnetic field, it basically picks up these ions and creates this giant torus around the planet. And this is called the Io plasma torus. It's full of these charged particles. But the plasma torus is in the plane of the magnetic axis of Jupiter, whereas Io is in the plane of the spin axis of Jupiter, which are different. And so Io is sometimes above the torus, sometimes it's below the torus, and sometimes it's inside of the torus. And this has a huge effect on what happens with the magnetic field, because the magnetic field connects Io and the plasma torus to the poles, just like we have the magnetic field attaching to the poles here on Earth. Now on Earth, that's one of the reasons that we have the aurora, is because charged particles impact the north and south poles. Exactly the same thing happens on Jupiter. we have these charged particles, they're interacting with the magnetic field, and they spin around the magnetic field lines in the upper right-hand corner you can see here, and they cause a thing that's called cyclotron radiation. And at the rate and the strength that they come off of Jupiter, they actually come out in radio waves between 10 and 40 megahertz. You can probably see where this is going. So here's an example of what one of the aurora looks like on Jupiter. This was actually taken in 2 different wavelengths. The aurora was taken in ultraviolet, and then the planet was taken in normal visual light. So this is not something you would see with the naked eye, but still the aurorae that are on Jupiter are pretty spectacular. So when you have these charged particles that are emitting radio waves as they cycle through the magnetic field, they put out up to a megawatt of radio energy. And sometimes that radio energy is pointed at the Earth and we can detect it. Sometimes at times that you don't want to detect it. So there are 2 types of radio waves that are emitted. One's called L and one's called S, because people love naming things in obvious ways. This is long and short. So I'm going to play for you an example of what these 2 sound like. And you can tell me if you've ever heard these things on your HF rig. Okay, so that's what an L burst sounds like, and this is what an S burst sounds like. So S bursts are actually kind of cool because what happens is they have a burst that comes out that changes its frequency very, very rapidly. It starts at a high frequency and it drops to a low frequency, and it goes through all of the intervening frequencies. So the reason that you hear that little pop is because that's where it went through the bandpass of the receiver. So it's only short from the perspective of someone who's receiving a narrow bandpass. It's actually a much longer burst just across a wider range of frequencies. So I saw Jim nodding his head there. Have you heard things like that on your HF rig while trying to make contacts?
I've heard more of the L than the S, yes.
Yes. Mm-hmm. Yeah, so I can't guarantee that what you heard was an L burst as opposed to some other sort of, urban noise, but, there's a good chance. So over a 25-year time period, people measured these bursts that were coming off of Jupiter and looked at the statistics of when they were easily detectable here on Earth. And they compared that with 2 main positional concepts having to do with Jupiter. The first one here on the horizontal axis of the graph is the position of Io relative to Jupiter itself. So this is where Io is in its orbit, basically what longitude of Jupiter it is over at a time. On the vertical axis here, we have the phase of Io as seen from Earth. So a phase of 0 is that Io is directly behind Jupiter from our point of view. 180 is directly in front of Jupiter, and then 90 and 270 are off to the 2 sides. And you can see that these are the probability here, where red is the most intense, of being able to hear one of these bursts on Earth, depending on where Io is in relation to Jupiter and in relation to Earth. And as you can see, there are some really obvious hotspots, right? So there are times you can expect to hear these things, and there are times that you cannot expect to hear these things. So about 10 years ago, I was taking a graduate course in radio astronomy, and as the class project, before we get into that, let me say one last thing. So why do we care about this? And there are a lot of reasons. The biggest one is that sending spacecraft to Jupiter is expensive, and the more that we can do remote sensing, the better. If we can learn about the magnetic field, we can learn about the rotation of Jupiter's interior, which is something that we can't see because the magnetic field rotates at that rate. The radiation environment at Jupiter, which is partially trapped by this magnetic field, is important because when we send spacecraft there, the spacecraft are going to be affected by the hard radiation that's present. So we want to learn more about it. We want to know how moons interact with magnetic fields. And we only have one set of data here on Earth about how magnetic fields and flux tubes and aurora happen, just like we only have one idea of how life happens in the universe. And when you only have one data point, it's really hard to draw generalizations. So people talk about the non-Earth physics. That doesn't mean that physics has changed its fundamental laws, but it means we get to see how it interacts in environments that we aren't used to looking at. And then the final one, which is actually really cool, is that there is at least one moon of Jupiter, Europa, which might have a subsurface ocean. Yes, this is the same one from 2001: A Space Odyssey. And the way that you want to look into a moon is you send a spacecraft that has ground penetrating radar, and then you look at the reflections. Well, sending a spacecraft with a high intensity radar transmitter is expensive. It requires lots of power and lots of room. But Jupiter is already a radar transmitter. It's already putting out all this energy all the time anyway. So all you actually have to send to Jupiter is the receiver. Jupiter can be the radar source. It can penetrate the ground of the moons, and then the spacecraft can receive the bounce back and actually see inside the moons using Jupiter as the illumination source. So no one has done this yet. It's a proposed idea, but I think it's a pretty cool idea.
Clever.
What was that?
Very clever.
Yes. So here's this little project that I did back 10 years ago for that radio astronomy class, where basically NASA puts out this little kit. It's really, really easy to build, as you can tell. And it's designed for schools, classrooms, things like that, where the whole class can build these kits together. And specifically, it just receives basically 20.1 megahertz, which is right in the middle of those bursts. And then you can take the audio output, you can listen, and you can say, hey, I hear a burst, or I don't hear a burst. So they tell you what type of antenna to build. So here's my house here in Sunnyvale. This is a phased dipole array that was pointed north-south, specifically aimed at where Jupiter was going to be in the sky at the time that I was doing this project. My front yard does not look like this anymore. My wife did not want to leave it up. Now my backyard looks like this, which is fine, but not the front yard. My wife has also a ham, by the way. But anyway, so how well did this work? So what I did is over a 30-day period, I monitored this for 16 days and basically looked to see how often I heard these S bursts. And then I looked at the event rates, which was number of S bursts per hour, and I compared it to where Io was in relation to Jupiter at the time, and just basically did a really, really stupid statistical analysis. So I had about 2 detections per hour when Io was in a good location that we should be detecting it, about 1.2 when it was in a bad location, and only about 0.34 when Jupiter was below the horizon.
Right.
So I thought that was pretty cool. I thought that was actually a pretty good indication that I really was hearing Jupiter and that I really was hearing these kinds of bursts. There was so much urban noise, though. I spent most of my project just trying to figure out where all the noise was coming from. And lest you think this is something that just the amateur, radio people do, this is just a histogram of the number of refereed and non-refereed journal papers that have been published since the 1960s that talk about Jupiter decametric radio emissions. And as you can tell, there's basically about 5 papers per year that have been published for the last 60 years on this as people learn more and more about how Jupiter's magnetic field works. So this is still a field of active research. People use the big telescopes like Green Bank and things like that to do this kind of measurement as well. All right, any questions about that before I move on?
Not yet.
All right, so it's gonna get deeper here. So going on to our second topic. One of the things that we really like to be able to do is see inside of things. And that's obviously very hard when you can't drill into them or take them apart. And astronomers are not really good at drilling into things that are far away. So how do you see inside? Well, one of the things you can do is you can use gravity. So when you have a spacecraft that flies by any sort of body, it is affected by the gravity, right? So it has some sort of arriving velocity, which has both a speed and a vector direction. It speeds up as you get close to the planet or other body. It slows down as you go away from it, but it changes its course. And how much it changes its course and how much it changes its speed depends on what the gravitational pull of that body is. By the way, the body itself also changes its speed based on the spacecraft flying by. So technically, every time we fly a spacecraft past a planet, we are robbing a very, very tiny amount of energy from its orbit. Luckily, it's very, very small. So anyway, if from this gravitational pull, we can tell what the mass of the body is. And then if we know the body's size, we can tell its average density. But average density is really only so useful because bodies are not homogeneous. They have all sorts of layers, like Jupiter we talked about earlier, and Earth with its core, its mantle, crust, atmosphere. And they also have non-uniform distribution of mass. So this figure in the bottom right is a globe of the Earth that has been distorted to indicate the level of gravitational pull at different points on the surface. So where it looks longer is where it has stronger gravity. Okay, so Earth is a very non-uniform gravitational field.
Wow.
So the question is, how can we measure this kind of thing at a level of precision that would give us something like this that we have for Earth, which of course we have all sorts of means of measuring locally, but we want to do this, to other bodies in the solar system. So just to reiterate, if we have a spacecraft flying past a body where the center of gravity and the center of mass are the same, basically there's a uniform gravitational field and there's a constant change to the spacecraft. But if the center of mass and the center of gravity are not co-located, then the gravitational pull changes. And so the spacecraft has a small change, and then it has a large change, and then it has a small change.
Excuse me. How much does Earth's gravity change over its surface?
I do not know because I research every planet except Earth.
Oh, God.
But
I
I know that it is very measurable, though. I mean, I know that you can walk around with a gravitometer in your hand, and you can actually measure the change in gravitational force. So it is non-trivial. And there are very noticeable masses that are below the surface that, even if you can't tell that the surface has a topology to it or, topography to it, there are still changes in the density below the surface that you can measure with basic surveying instruments, basically. So that does not give you a quantitative answer, but it gives you basically an answer that we have good technology, if nothing else. So the way that we measure Earth's gravity, by the way, I'll just divert just for a second, is that we had two spacecraft. They were called GRAIL, Gravity Research something laboratory, I forget. And they were in orbit about the Earth at a very precise distance. And they had a laser interferometer connecting the two of them. I think it was laser interferometer, not radio. But basically, as they orbited the Earth, and one of them would go over a mass anomaly before the other one, their orbits would very, very slightly change. And so the distance between the spacecraft would very slightly change. And you could measure that using the interferometer that was present between the two spacecraft. And so they orbited around the Earth for many, many years and produced a very, very detailed map of Earth's gravitational field. Then we sent a duplicate of the same spacecraft to the moon, and we actually have a very detailed map of the gravity of the moon as a result. All right, so where does radio come into all this? Obviously, the way that we measure the change in a spacecraft's velocity is with Doppler shift. And there are lots of ways that we can do this. So some spacecraft have an ultra high accuracy oscillator inside of them and send a precise carrier signal back to Earth. Others, like Cassini, which we'll be talking about later, they receive a precise carrier from Earth, then they have a transponder that frequency shifts it, and then they send it back to Earth. Okay? The ground-based receivers are pretty sensitive, although if you actually work out the math, you would say, wait, they could be better than this. But we're talking really long distances. Remember, we're talking about like 4 hours of light travel time here. So the noise and the signal strength, leaves a lot to be desired. So we can measure about 0.02 millimeters per second and change, but there's lots of distortion. We have to worry about the atmosphere here on Earth, the ionosphere. We have to worry about plasma that exists between the Earth and other planets. And then we also have to take out things that could be causing the spacecraft to change velocity that are not related to gravity. So for example, the solar wind actually puts pressure on spacecraft. That's why you talk about solar sails as a way of, doing spacecraft propulsion. A lot of our spacecraft have what are called radioisotope thermal electric generators, which are basically plutonium pellets that emit heat, and that's their power source. When you get far enough from the sun, you can't use solar panels effectively anymore, so they're nuclear powered. So you get waste heat from the RTGs, and that actually changes the velocity of the spacecraft. It's basically a type of propulsion. Likewise, you have gravity from other nearby moons, rings, other planets, and you have to subtract all of that out before you can get the gravitational pull of the body you actually care about. So doing this is very, very difficult. I have no idea all the details of how this happens, but I have a great deal of respect for the people who have figured all of this out. So the first thing you do is you measure the gravitational field. Ideally, you do it frequently so that you measure it at various points during one flyby, not just once at the end, so that you can get more fine-grained data. You want to do more than one flyby if you possibly can, because if you're trying to get a three-dimensional idea of what the gravitational pull is, you need to sample different latitudes and different longitudes of the body, and you can't do that with just one flyby. And unfortunately, not every flyby is capable of measuring gravity. And the reason is that there are other scientists who want to do other things with these spacecraft. And the way the spacecraft are designed, the instruments are usually rigidly mounted on the spacecraft body. And so if you have one instrument that is pointing at something, the other instruments are probably not pointing at anything useful at all. They're pointing off into space. To do gravity measurements, you need to have the main transmitting antenna pointed at Earth so that you can do the Doppler shift measurements. But at the same time, that means that you can't be doing other measurements because those instruments are probably not pointed anywhere useful. So there's a lot of trade-off in the science planning between the different teams, basically arguing over whose science is most important at a given point and how much time they should be given on the spacecraft. From my point of view, it's always the people doing rings research. Always.
Of course.
All right. So once you have all of this, you can, it doesn't, having the gravitational field doesn't give you quite all the information that you need. You really want to deduce the moment of inertia. And this requires a lot more physics and math I'm not going to go into. But basically, you can take the gravitational field and combine it with a model. And that gives you a guess at what the constraints are. So for example, here is a very simple 2-layer model of the moon Ganymede around Jupiter. There's a rocky core and there's an icy shell, and they have different densities. So here's the possibility of the rock densities. Here's the possibility of the ice densities. And if you draw the contour lines, you end up with the ratio between the diameter of the rocky core and the diameter of the ice shell, because we know how big Ganymede is as a whole, and we know what its overall mass is, okay? Once Galileo, the spacecraft, flew by it, it was able to deduce that the moment of inertia gave this constraint, plus or minus error bars, okay? So it said that all the rest of these things here were not plausible models. And in particular, something that wasn't a plausible model was that it was just uniform, that it had to be differentiated into a rock and an ice. And so I'm going to quote various papers as we go along here, but here was the paper that was published on it saying that it clearly shows that Ganymede was differentiated into a core and a mantle. They have an idea about how big the metallic core is, 400 to 1,300 kilometers, surrounded by a mantle, which is enclosed by an ice shell. So they figured all this out just by looking at this constraint on this very simple model. Okay? We still don't know precisely, but at least we have a much better idea of what's going on now. All right, now to my favorite topic, Saturn's rings. So I'm sure everyone has seen Saturn rings. In fact, if you look in a decent pair of binoculars, you can actually just see them in your backyard. And they look interesting from the ground, but they don't look as interesting as they really are, because Saturn rings are very, very complex. It is not just one ring. It is not just a uniform platter of material. It is a collection of countless particles that are made primarily of pure water ice that are all orbiting individually and all colliding with each other, breaking apart and recombining. And there are different regions of the rings that have different sizes of particles in them and different levels of contaminants and different colors. So the main ones you can see from Earth, just looking through a halfway decent backyard telescope, are the A ring and the B ring. Again, scientists are really good at naming things. These are named in the order of discovery. In between them is actually another ring that looks dark from Earth, but actually is full of very small ring particles that you just can't see because they don't reflect light back towards Earth. That's called the Cassini division. Then there's some much finer rings called the C ring and a dusty ring called the D ring inside, which we'll talk about later. And then there's this little tiny ring on the outside here called the F ring, which I've spent many years of my life researching. That's my favorite ring. And then we have this big diffuse E ring, which we will talk about Enceladus here in a moment. But anyway, just the point is that the rings are very, very complex. And it's very important to remember that every ring particle is on its own orbit. This is not like a record where they are all in lockstep with each other. They're all at their own orbital speeds. In fact, it was James Clerk Maxwell originally who did the math to realize that they could not be a uniform, coherent disk, that it was impossible for them to rotate. They would break apart under their own stress if they were their own, a single uniform disk. So my favorite spacecraft, and if you saw me earlier, I'm wearing the shirt from the mission, is the Cassini orbiter, which was the largest and heaviest spacecraft ever sent to the outer solar system. It weighed over 2 tons and was 21 feet tall. If you can see here to scale, these are people who are working on the spacecraft. Basically, it's the size of a school bus. It was launched in October of 1997, did a very circuitous route to get to Saturn with many flybys of Venus and Earth, and arrived at Saturn in 2004. It was busy once it got there. So NASA has a tendency to over-engineer things. If you're familiar with the Spirit and Opportunity rovers on Mars, they were designed to work for 90 days. They worked for 10 years. You laugh, but this is actually a problem because you have to pay for all these extended mission time, right? There have to be mission control people. There have to be scientists. And whenever you have people paying for old missions, you don't have money for new missions. So there's always this fight between, do you kill the old missions that are still working to have money for the new missions, or do you keep the old missions going because they're actually useful and then postpone the new missions, right?
Still working though, don't you?
Yeah, but so, there's a lot of, there's always a lot of budgetary stress. So Cassini was designed to be in orbit around Saturn for 4 years. Okay, it was there for 13. So there was the initial 4 years, which was the primary mission. And these are the orbits that were done. The original, there were 75 orbits around Saturn that were done during those 4 years. Okay, you can see that they changed orbit a lot. That's so that sometimes they could be looking at moons, sometimes they could be looking down on the rings. So they needed to look from different perspectives. Changing the orbit this often takes a lot of fuel. And unfortunately, there's only so much hydrazine that Cassini was able to carry with it. So then they said, well, it's still working fine. So let's do a second mission, which they called the equinox mission, okay, because it occurred during Saturn's equinox. This was during the time that the sun was edge on to the ring plane. And so anything that was a very slight vertical bump in the rings cast a shadow. And you could actually see things about the vertical extent of the rings. And that's beyond what we're going to talk about today, because there's nothing to do with radios, but I have some talks that I give on that I love how that affects the rings. So anyway, so that was another 2 years. And they said, well, Cassini's still working just fine, but we're running out of fuel. So they did 155 more orbits in this later thing that they called the solstice mission, because it went all the way to Saturn's next solstice. But these were orbits that they didn't change very often because changing orbits takes fuel. Okay, so you were more limited in what kind of science you could do, but we still got great data out of it. So anyway, this is just, the people who plan the orbits for these things, are really pretty incredible. So one of the moons that Cassini flew by many times is this moon called Enceladus. Enceladus is one of the icy satellites, and one of the more interesting ones, I think, because it is covered by these fissures that are called tiger stripes. Okay, and it has a very different look to it than any of Saturn's other moons. And if you look at it in the correct, and these are real photos, by the way, if you look at it in the correct light with the sun shining behind Enceladus, what you see is this. There are actually geysers that come out of the south pole of Enceladus. And again, these are actually actual photos. These are not artist renditions. So this stuff that's coming out of it, no one knew about or knew what was in it until Cassini was there. And Cassini was actually able to fly through these geysers. And even though it didn't have a mass spectrometer on board, it did have some instruments that were designed for doing things like a cosmic dust measurement and charged particle analysis. And so they were able to do some analysis of the contents. And what they found is that there were organics, volatile gases, water vapor, carbon dioxide, carbon monoxide, potassium and sodium salts, and silica. So basically, it sounds sort of like a saltwater ocean with a rocky base to it. Now, we love water on other bodies because wherever you find water on Earth, that's where you find life, right? And NASA's motto is always you follow the water. You look for water on Mars, you look for water on any other planet, and you look for water here on Enceladus that might be liquid, because that means there might be life there today. Okay. So obviously it's an open question, but it's a very interesting one. And one of the things that you want to know is what's below the surface that is producing these plumes. So there's a model, of course, of what people think might be there. There's this ice crust, there's this global ocean, and then there's this rocky core. But how do you actually look inside? Well, we use gravity. So Cassini did a number of flybys of Enceladus and was able to produce this comprehensive gravity map of the moon. So red is where the gravity is stronger, blue is where the gravity is weaker. And you can see that there is this, what they call a negative mass anomaly at the South Pole. Okay, so it is less dense at the South Pole, and it is more dense than average at the North Pole. Now, we know the plumes come out of the South Pole, so this could be a little bit of a smoking gun as to why the North and South Poles are different. They don't both have plumes because one of them has mass more than the other. But what does that mass actually mean? It's really hard to tell what causes mass, right? Because again, you have to have models that you match. So I'm not going to go through all the models that people came up with, but I am going to give you their final conclusion here, which is that gravity data can't rule out a global ocean, but what they really prefer instead is that there's a regional sea. And this is not just because of the gravity anomaly, it's also because there are some temperature differences between the South and the North Pole, and it's also because of the shape of Enceladus and how it changes during its orbit. But you put all those things together, and they think that maybe there is a local sea under the South Pole, but not a global ocean. So this is pretty important if you're going to send a spacecraft there in the future to go investigate the sea, right? Don't send it to the North Pole because there might not be a sea there, right? Send it to the South Pole. So another one of Saturn's moons is Titan, and Titan is another very strange body in that it is the only moon in the solar system that has a substantial atmosphere. The atmosphere is primarily nitrogen, it's about 94% nitrogen, and it's 6% methane. And you can't see through it in visual light, so people had no idea what the surface looked like. But it is possible to see through it at certain frequencies of infrared, and you also can look through it with radar. And Cassini had onboard radar, which we're not going to talk about today, that was actually able to do some mapping of the surface. And this is what you see when you look through with infrared and radar. Okay. Those dark areas are lakes on the surface of Titan. Now, they're not water lakes because Titan is far too cold for that. They are methane lakes because the temperature and pressure at the surface of Titan is basically at what's called the triple point of methane. So methane is able to exist as a gas and as a liquid simultaneously. So you can have a methane atmosphere and then you can have a methane lake, just like we have water vapor in the atmosphere and we have a water lake here. Okay, so we don't know of life that can exist in liquid methane, but it is a heck of a lot of organics available to produce interesting molecules. So again, it's another point of interest. But is there water, and is there water below the surface? Again, we can do the same kind of trick with the flyby, but we do it a little bit differently this time. Titan, as it orbits around Saturn, is in a more eccentric orbit. So sometimes it's closer to Saturn, and sometimes it's further away from Saturn. And this means that the tides that Saturn raises on Titan change depending on when it is in its orbit. Sometimes Titan is squeezed a lot, sometimes it's squeezed just a little bit. If you look at how Titan changes shape as it goes around its orbit, sometimes it's more spherical, sometimes it's more like an ellipsoid, you can basically tell how elastic the interior of the moon is. And different materials have different elasticities. So a global ocean would have one type of deformation characteristics, whereas solid rock or solid ice would have something else. So what they did was they did flybys of Titan at different points of it in its orbit, did gravity mapping to see what shape it was, and then used that to determine the elasticity of the interior of the moon. And so again, here's an artist's rendition of what the interior of Titan might be like with all these different layers. And what they came out with was that it is physically unrealistic for Titan to be entirely elastic, which means that it was entirely made of rock or ice. Our results strongly suggest that there's some global layer within Titan that's behaving like a fluid on orbital timescales. And then there's various ways that could happen, but certainly one of them is a low viscosity layer, an ocean beneath the ice shell. So unlike Enceladus, which may only have a regional sea, there's a pretty good chance that Titan actually does have that global ocean. Now, what's in the global ocean, we don't know, right? We don't know what kind of liquid is in there, but given that things are made out of a lot of ice in the outer solar system, water is not a bad bet. And if there's water, once again, another good place to look for life. So I'm emphasizing the life on Enceladus and Titan, not just because I work for SETI and because we like looking for life, but because it's going to have an interesting implication on the Cassini mission here in just a moment, which is Cassini started to run out of fuel. And what do you do with a spacecraft that you're going to lose control of? Well, sorry?
Put it someplace useful.
Put it someplace, you could put it someplace useful, but you would need enough fuel for it to leave Saturn's orbit if you wanted to put it somewhere safe in the solar system. Because the problem is, if you let it orbit around Saturn, there are enough gravitational perturbers, meaning lots of moons, for example, that eventually you can't guarantee that it wouldn't crash into the surface of either Enceladus or Titan. And Cassini was not sterilized at the level that you would want it to be sterilized at to protect other life from Earth microbes. And we know that Earth microbes can live through an amazing amount of crap. You know, they can live in outer space for a long time. So they needed to make sure that Cassini, under no circumstances, crashed on the surface of Enceladus or Titan. And the only way to guarantee that was to have a controlled destruction. Okay, now this is different from a lot of other spacecraft, which are orbiting planets where we don't think there's life, or where they're simply out in the solar system and there's nothing that they're likely to crash into, right? But here at Saturn, the odds were just against us. So they thought long and hard about it, and they said, we can come up with a set of orbits that actually start. There's this really eccentric orbit here that goes just outside of the rings. And then they do one maneuver, and in that one maneuver, it hops from the outside of the rings to the inside of the rings. And Cassini actually had 22 orbits that passed between the innermost ring and the surface of Saturn. And this is really like threading a needle. There are only, we're talking a few thousands of kilometers of space here. And no one had any idea what was in there. I mean, we knew there weren't, moons and things like that, but we didn't know if there was ring material. And if you have a spacecraft that is flying really fast and it hits a grain of ice, it's going to do serious damage to the spacecraft. So they designed it in such a way that if after this first orbit, they lost control of the spacecraft and they could send it no more commands and have no more trajectory adjustments using fuel, that it was guaranteed to crash into the surface of Saturn no matter what. Very, very clever. Okay, but obviously we could do lots of really interesting measurements passing through here that have never been done before in human history. So I was peripherally on the Cassini mission team. I was one of the 3,000 people associated with the mission. And at the end of mission, which happened on September 15th, 2017, at 4 o'clock in the morning, they invited us all to come down to Caltech and watch the destruction of the spacecraft. Now, they couldn't host us all at JPL because JPL was busy doing mission control and it wasn't nearly big enough. So they put us out in, I don't know what you call this at Caltech, the equivalent of the quad, with these big screens. This is the middle of the night. And this is all the Cassini scientists and all of their families were invited to come down there and spend the night and watch the end of mission. So I managed to film the end of mission with my phone. And this is 2 carrier signals that were coming down from the spacecraft. One's X-band. This is about an 8 gigahertz carrier. And this is S-band, which is about a 2 gigahertz carrier. And they're both being transmitted to Earth at the same time. But because they're different frequencies, they have different refractive properties as they go through Saturn's atmosphere. So as Cassini was going to descend into the atmosphere and eventually burn up, the signals got diffracted at different, or refracted, I guess, at different rates. And so we saw them go away from Earth at different times. So here is the end of Cassini.
Cross the 0 time.
So you can see the X-band starting to waver a little bit. And there it went away. And here's the S-band going away.
Go ahead, Flight Director. We have lots of signals in X-ray band and zero band.
And then for everyone who managed to stay the entire night, they gave us donuts the next morning.
I love it.
What's most disturbing about this image is that all the donuts are still there and all the people are gone.
Yeah.
Oh,
So yes, we did stay there the entire night. All right, so anyway, so normally when you have something like Cassini flying by a ringed planet, the flybys happen far outside of the rings. And so the rings and the planet get mushed together into one gravitational pull, and you have no way of separating them out. But if you have the spacecraft going between the planet and the rings, all of a sudden you are now able to separate those 2 pulls out. And you can do things like measure the gravitational pull of Saturn and the gravitational pull of the rings. And that latter one is particularly interesting, which we'll talk about in a minute. So, okay, so one of the things about Saturn is that just like Jupiter, its atmosphere has differential rotation. So if you can see here, this little graphic, you see how different parts of the atmosphere are rotating at different rates?
Yeah.
Right? Some of them are moving really fast and some of them are moving really slow. Jupiter does the same thing. And if you think about what happens when something spins, is it gets wider, right? And if something spins faster, it gets wider still. So Saturn's atmosphere is not a sphere because different parts of the atmosphere are rotating at different rates, and the parts that are rotating faster end up bulging out. Okay, so if you go back and look at this, diagram here, you can see that they, we've drawn different parts of the atmosphere having different gravitational pull as Cassini goes past it, right? And that's because different parts were orbiting or rotating at different rates around the planet. So as you do your analysis of the gravity, this now allows you to model the interior of Saturn and figure out how far down this differential rotation happens. Because it doesn't go down all the way to the core. This may be a surface phenomenon, right? And then you just have solid or viscous stuff beneath it. So here is a somewhat complicated looking graph that I will explain to you, which is so first of all, the x-axis is basically the equivalent of a Fourier decomposition of the gravitational field. So these are harmonics, okay? And as you go higher in harmonics, you get finer grained in the changes in the gravitational field. The even ones are things that are symmetric between the north and south hemispheres of Saturn. And the odd ones are cases where the north and south hemisphere are asymmetric, that one is stronger than the other in its gravitational pull. So if you had a uniform rotation of all of the atmosphere, these diamonds show you what you would expect. The green circles are what was actually measured. And what you can see is that as you get up into these higher harmonics, they diverge. Okay, and that means that the atmosphere does not have uniform rotation. And the second thing that you can see is that you would expect the odd ones to be 0 if it was symmetric north and south, but they are clearly not 0. And that shows that there is a north-south asymmetry in Saturn's atmosphere also. So if you put all this together and do a model, you can measure how deep the atmosphere rotates. And the answer is that it extends to a depth of about 9,000 kilometers below the visible surface of Saturn. Whereas Jupiter, which has the same kind of differential rotation, is much shallower at only about 3,000 kilometers. Okay, then they can also deduce that Saturn has a core of some kind at its center, with a mass of around 15 to 18 Earth masses. But enough of planet. Yeah, go ahead.
Sorry, I couldn't unmute myself in time. Rewinding back a little bit, you were talking about crashing into Cassini. Was that planned as part of an extended mission, or was it not originally planned, or what was the original plan as to how Cassini should end?
It was definitely planned as part of the extended mission. I honestly don't remember what the original plan was. That was so long ago at this point. And also I'm not sure that they had as much information at that time about that they needed to protect Enceladus and Titan, because most of what they learned about Enceladus and Titan came from the Cassini mission.
Oh, I was confused.
Oh,
on that
that's interesting.
So,
question?
yeah.
So Enceladus and Titan, so they did not want it to touch those planets, but it was okay to crash into Mars in the sense that if there were microbes on board the Cassini, then they probably wouldn't survive anyway, right?
Did you say Mars?
I'm sorry, Saturn. Sorry.
Saturn, yes. Yeah. There was no expectation that there was any sort of life in Saturn's, hydrogen, helium, atmosphere. Maybe there could be. That's certainly the realm of many science fiction books. But there is no knowledge of life that can exist in that kind of environment. So they consider that to be a safe place to contaminate.
When Cassini crashed into Saturn, did a blemish appear as happened when the comet crashed into Jupiter?
Not that I'm aware of that we could see. I think that the amount of energy difference was huge. Between the comet and Cassini. Cassini, it's the size of a school bus, but we're talking about a planet that's 13 times the size of Earth. So it's sort of like asking whether or not when you crashed your car into a telephone pole down the street, did a blemish appear on the surface of the Earth that was visible from 5 light hours away? So, right. I think the answer is probably we could not have seen it.
Bigger school bus next time.
Yeah, bigger school bus, exactly. Bigger rocket. And like I said earlier, Dick Simpson's on the call. So Dick, if you have anything to chime in with earlier in the Cassini mission, feel free. All right, but anyway, enough of planets. Let's talk about the fun stuff, which is rings. So one of the greatest mysteries in the entire solar system, from my point of view at least, is how old Saturn's rings are. Everything in the solar system that you see is basically 4.5 billion years old. And it was all formed at basically the same time out of the same primordial soup that formed the sun, all the planets, and all the moons. Okay. You would like to think that Saturn's rings formed at the same time. Okay. But there are two competing issues that can't both be true at the same time. Okay, the first one is, and you may not realize this, all 4 of the outer planets, Jupiter, Saturn, Uranus, and Neptune, have ring systems. Most people have never heard of the other rings because they aren't nearly as spectacular. And one of the reasons that they're not as spectacular is they're basically solid black. They're really, really hard to see from Earth. They're also much smaller, but even given that, they are just not reflective. Whereas Saturn's rings are this pure white reflective ice that is just so, it's like having a mirror up there, right? So why do 3 planets have black rings and 1 planet have white rings? right? And the truth is that we would expect them all to be black. And the reason is that there are lots of types of interstellar dust and little meteoroids that are constantly impacting the ring surface. And those are all dark. And so you would expect this basically pollution to coat the surface of the ring particles over time and over a pretty short period of time and darken them so that they no longer look like pure water ice anymore. Okay. So this is an argument for the rings being new because they would not have had time then to become dark with this kind of impact. Okay. So let's say they formed recently, but the problem is that you have to postulate that there is some sort of icy body, and a pretty big one, the size of one of Saturn's moons, that was captured by Saturn and torn apart by Saturn's tides in such a way that it formed the ring system. And first of all, dynamically, it's really hard to actually get Saturn to capture something like this and tear it apart. And second of all, there just really aren't that many bodies hanging out there anymore. There were a lot of things happening earlier in the solar system where things were crashing into each other all the time, but there's just not that much, Shoemaker-Levy notwithstanding, that's a pretty rare event, right? And that was nowhere near big enough to form a ring system around Jupiter, right? So, there's this argument that goes back and forth about which one of these things could possibly be true. And I won't go into the details of it, but there is this concept that if the rings have a relatively low mass, then they are probably young. And the reason is that the rings have a way of recycling themselves to basically allow their interiors to become their exteriors and thus expose their clean core. But that only works well if they have a lot of mass that they can recycle over time. Okay. So how do we determine the mass of Saturn's rings? Well, you fly a spacecraft between the rings and Saturn, and now you subtract off the gravity of Saturn, and you've got the gravity of the rings. And for the first time in human history, you know what the total mass of the rings is. And the answer is it's about 1.5 times 10 to the 19th kilograms, which is just a little bit less than half of the mass of the moon Mimas, which we will see more of in a moment. And that sounds like it's a lot, but that's 1% of the mass of all of Earth's oceans. So, enormous rings, relatively little mass, all things considered. And in fact, this is at the lower end of the predicted range for the mass of Saturn's rings. Okay, so this once again is reinforcing the concept that they are young, probably just 10 million to 100 million years old, which is very young in astronomical time. Okay, however, we now have the problem that we don't know what could have broken up. And so now people have to postulate that there was some kind of body that had a chance capture and a tidal disruption, that happened much more recently. And that means that such bodies have to exist much more recently than we think they did. So, once again, you have fighting models. This doesn't answer the question, but it's yet another thing that points in the direction of a young ring system, which in many ways is much more interesting than an old ring system, right? Something that actually formed recently is fascinating. All right, anyway, moving away from rings for one slide, I'm going to talk about radio occultations. And occultation, so actually, before I go on, any more questions about that last subject before we head on? All right.
A lot of information that you just, to those of us who are not in this area of expertise, it's just amazing.
Yeah, I know this is there's a lot of stuff in this talk. I kept thinking I should make it shorter to make it a normal length talk. And then I kept saying, I can't think of anything that I want to cut out. So,
Give us the full
so my apologies if you have to, go and go to bed or something. I won't hold it against you. All right. So radio occultations are any time that an object passes between the radio source and the observer. And there are two things that can happen when you have an occultation. One of them is that the wave can be diffracted or refracted by the body. And the second one is that it can be attenuated by it, right? And both of these are things that we're well familiar with as hams. So one of the things that you can do is you can pass a radio signal through an atmosphere. And the charged particle density in the atmosphere changes the refraction and affects the Doppler shift of the radio waves, which you can then measure at some receiver. So I'm going to do this very, very briefly here. The European Space Agency has this spacecraft called Mars Express, which is one of the myriad spacecraft currently in orbit around Mars. And they did a series of measurements of the atmosphere of Mars, which it does have one. And if you haven't heard the sound from the helicopter on Mars, by the way, which NASA just put out, it's really fun. Just look up on YouTube. They the Mars Perseverance rover has a microphone on it. And on the most recent helicopter trip, they recorded the sound of the helicopter blades as the helicopter flew around Mars. Yeah, that was just really cool. And I just saw that today for the first time. So anyway, so they discovered that one of the things that you can measure is the ionosphere of Mars's atmosphere. And they discovered that there was a third layer that they didn't know about previously at the bottom of the ionosphere, but that it was sporadic and it was geographically isolated. This was basically like a sporadic E layer. Okay. And the hypothesis was that it was formed by meteors, just like the E layer is formed on Earth. And so a number of years later, there was a comet that went by Mars. It was called the Sliding Spring Comet, which always sounds like a strange name to me. And the debris from the cometary tail impacted the Martian atmosphere. And they were able to measure the change in the ionosphere as the cometary dust impacted the atmosphere, and basically prove this hypothesis that they'd come up with years earlier as a just a result of this one measurement. So that was kind of nifty. So if you were on the ground in Mars, you actually could probably do, meteor scatter communication. But back to rings. Okay, so the other thing that you can do is that you can fly a spacecraft behind the rings, and then you can send the radio signal to an observer on the other side of the rings. And as the spacecraft flies across the rings, the amount of attenuation that you get changes based on what the characteristics of those ring particles are. So if there's a really dense set of ring particles, it will attenuate more, and it will attenuate differently depending on the size of the ring particles relative to the wavelength of the radio waves that are being sent through. So Cassini did many of these occultations. Many of them were radio, some of them were also in visual light or in ultraviolet. We're going to talk about the radio ones. But the problem is that you only get one slice through the rings. And so if you want to come up with a 2D structure, you have to do a bunch of slices at different points on the rings. But luckily, Cassini did 204 of these radio occultations across the ring planes during its time there. Okay, and this is an example of what's called an occultation profile, where on the x-axis we have the radius. This is how far we are away from the center of Saturn. And then this is what's called the optical depth, basically how much the signal was attenuated. So 0 means there was no attenuation. And then basically these are powers of E as you go down. So, call this a factor of 2.5 in the attenuation of the radio signal. And you can see the detail of the structure of the rings that you can see. This is not noise. This is actual real structure in the rings. And you can see as we go through different parts of the rings, from a D ring to C ring to B ring to A ring, how different the density of the material in those different parts of the rings are as well.
How consistent is the density of a given ring around its diameter?
Very consistent. Although there is fine grained structure, which is what we're about to talk about. Rings tend to mix. There are constantly collisions, and it's very hard for, for example, if you had a dense part of the ring that is orbiting around Saturn, that's going to collide with other parts of the ring that are less dense, that are traveling slightly faster or slightly slower. And it takes very little time for that to all break apart and even out. It's the same reason that the vertical height is so thin, is that anytime a particle tries to extend itself vertically, as it goes back through the ring plane on its orbit, it ends up impacting with other ring particles, and they end up dampening each other out. So you actually can't have crossing rings, for example. They disappear almost immediately because of these mutual impacts. So the structure, though, here is a little tiny section of the rings, this little area right here, blown up. And again, this is an actual photograph. And you can see the kind of structure that you have in the rings. Okay, you have gaps, you have little ringlets, you have waves, you have changes in density, right? All sorts of interesting structures. So here's an example where the density does change as you go around the rings, because these are actually waves that are existing in the rings. The rings are dense enough that they actually act like a fluid some of the time. So you can actually impact part of the rings and waves will expand out from that point, just like they would in a body of water, for example. But these waves that you're seeing here are not caused by impacts. These are caused by the gravitational pull of other moons. So these are what are called resonances. So you know what a resonance is in ham radio, obviously, why you have a resonant antenna or resonant LC circuit, that basically there's a characteristic frequency that if you stimulate the system at that frequency, magic occurs, right? And if you stimulate at some other frequency, nothing interesting happens, okay? So what happens here is that we have even ratios between the orbital period of some moon, in this case, it's Prometheus, for example, here, or Pandora, and the ring particles at this particular distance from Saturn. So in this case, the ring particle orbits Saturn 17 times. Every time Prometheus, which is out here on the right somewhere, orbits 16 times. And as long as these are an integer ratio, the smaller the better, but 17 to 16 still works, this ring particle will get a little kick every time at just the right spot. And something interesting will happen. And there are lots of different types of resonances, and I can't go into all of them, but sometimes it will open a gap. Sometimes it will cause higher density. Sometimes it will cause waves. Okay, so these waves here are caused by the moon Mimas. The ring particles are orbiting 5 times for every time the moon is orbiting 3 times. Okay, and actually there are 2 different resonance spots. These are called density waves, and these are called bending waves. These are actually waves that are vertical, whereas these are changes in the density of the ring particles. And we're going to look at these. But the interesting thing is that, I don't know if you've ever seen Mimas, but Mimas is basically the Death Star. So, which is sort of appropriate since, we were just came off of a Star Wars Day with the, May the 4th be with you a couple days ago. But anyway, this is the moon that is causing these perturbations in the rings. And of course, it's way out here outside of the rings, but it has more than enough gravitational pull to have these effects. So this is an example of,
how did you know that it was causing the effects in there, not all the other effects everywhere else?
Well, you look at the resonances. So you basically map out, how fast the ring particles are traveling, how fast Mimas is traveling. And you look at every possible integer ratio between the two for every possible moon. And a lot of them have things that are happening in the rings. So I'm only looking at one little tiny section of the rings, and I'm showing you one tiny section of the possible resonances. But if you looked at the entire rings, you would see all of the different resonances. There's the 1 to 2 resonance, and the 2 to 3 resonance, and the 1 to 3 resonance, and the 2 to 5 resonance, and the 3 to 5 resonance, and the all the prime rationals are going to have some effect if they occur inside the rings. But the moons are at sort of random locations in terms of their distance from Saturn. And so it would be pretty weird for the Mimas 5 to 3 to be on top of, the Tethys 7 to 3 or something, right? They don't occur at exactly the same spot, right? So, all these different resonances occur at different locations. So there's really only one choice for what could be causing those features. Does that make sense?
Yes, thank you.
Okay. All right, so this is just an example of what a spiral density wave looks like. This is obviously as a galaxy, just like the Milky Way. And what happens is you have certain areas that are more dense, and you have certain areas that are least dense. And I always say that the way that you can understand this as a normal person is if you go out and you drive on the freeway and you have every car drive exactly the same speed, what happens?
I'll bunch up.
You all bunch up, right? And the reason you all bunch up is because you're never traveling at exactly the same speed. There was this great video that I saw once. The Japanese researchers had put cars on a circular track with automatic control of exactly how fast they were going. And it took like 2 turns around the track before there was a traffic jam. And that's what happens in galaxies, where you have these spiral density waves that are basically dust bunching up. And whenever dust bunches up, that's where you get stars, because stars are basically a bunch of dust that comes together and ignites. Right? So wherever you have lots of dust, you have lots of stars, and in between, you don't. Okay. But we have exactly the same thing in Saturn's rings, right? This is a spiral density wave. We're only looking at a little tiny part of it, so it's kind of hard to see. But we can look at the whole thing using these radio occultations. So if we do a whole bunch of these radio occultations across the rings over time, we can basically make a 2D map of what a structure looks like. And we don't have photos of this. We have to reconstruct it using these radio techniques. This is a really oddly distorted graph, okay? The distance between the center point right here and the edge of this black line is 132,000 kilometers. The distance between this edge of the black line and this edge of the black line is 250 kilometers. Okay, so this is deeply distorted because we only care about this area of the ring, which is where that density wave is. But if we drew it to scale, my PowerPoint presentation would have to be the size of Sunnyvale. Okay, so they do this distortion where the inner part of it is at a totally different scale to the outer part of it. Okay, so here is the exact location of that 5-to-3 resonance. And then the wave is going to start there and it's going to propagate outwards from that. Okay, so what you do is you take all of these different cuts basically, and each one of them looks like this. So as you're, if you go back, if you think about what this looked like, right, it's a whole bunch of little increases of density at different periods between them, right? This is not evenly spaced. They get closer and closer together. And so when you do the radio occultation, this is exactly what you see. Increases in density that get closer and closer together. Okay, and that's just one slice. So you take a whole bunch of these slices, you interpolate between them, and you get this. So this is the same distorted scale we were looking at before, where this is 130,000 kilometers, this is 250 kilometers, this is the resonance location, and you can see how the wave is propagating out from it. Okay, but this is basically what the wave looks like in 2D, and this is not a model. This is actually what it was measured to be with just interpolation between the measurements. And just to give you a little example of how accurate this is, I went on the web and I just found a photo of the close-up of the density wave, and I just photoshopped it in. I didn't do much effort to try to make it match properly because the big one is taken looking down on Saturn, but the image of the ring is taken at an angle, so it's distorted, right? So I didn't try to de-distort it properly, but you can see that I basically managed to get it to line up properly. Right, so this is the photo and this is the radio model. Oops.
Nice.
All right, we have one more subject to go. Any questions before we move on?
This stuff boggles my mind, Rob. It's just amazing that you figure this out.
Well, other people figure this out. I don't figure most of this out.
This is Alex. I had a question about the rings width. You said it's like 30 feet.
Correct.
What's keeping it to be 30 feet? How come it doesn't like diverge due to those collisions that you talk about that internally happen? So the thing you have to realize about orbits is that orbits are always planes, right? There's always, orbits don't turn in the middle and go like down and then up again or something like that, right? So if you think about an orbit as being like, let's say, an old vinyl record or a CD or something, right? Then if a particle is orbiting, it's going to be sometimes up and sometimes down if that record is tilted with respect to the equator of the planet. And then if you have some other particle on some other orbit that's tilted differently, they must cross each other, right? There's no way that one of them cannot cross the other, right? Sure. So when they cross, they are going to hit each other at some point, the particles. And when you have a particle that's going down, impacting a particle that's going up, you have to conserve momentum, right? And you end up with an average momentum, which is neither up nor down, but is somewhere in the middle. Okay.
Right? And so if you look at that as a process that happens trillions of times to all these particles over time, every time they impact, they're basically averaging out their momentum.
Oh, I see. Okay.
And in the end, they all end up they have to be in the same plane. And there are some more complicated things happening due to the fact that all these planets are oblate. Their equators are bulged out, just like Earth's are, because they're spinning. And because we talked about earlier, when a planet has a bulged out center, its gravitational field is not uniform. And there's some very interesting things that happen to orbits when they're orbiting in a non-uniform gravitational field that actually ends up forcing the rings to always be lined up with the equator.
Oh, okay. Interesting.
And I'll just hand wave and say that that's true. But that way you don't get a flat ring that is offset from the equator, that is tilted with respect to the equator. It's always lined up with the equator.
Sure. Okay.
Because it's not a sphere.
Sure. Thank you.
Mm-hmm. Anything else?
I think we're ready for radar.
All right, here comes radar. Okay, so radar, I'm going to talk about radar being sent from Earth. And, there were two classic radar dishes that everyone thinks about. One of them is the Goldstone Deep Space Network DSS-14 dish, which is down in Southern California. And the second one is Arecibo, may it rest in peace. And of course, I won't go into great detail here about Arecibo's demise. Everyone has already seen all those videos, but it was a very sad day for the astronomical community. So Arecibo had a 300, I'm sorry?
Very, very sad.
Very sad. Very sad, yes.
Was that the one in Puerto Rico, or was that?
Yeah, that's the one in Puerto Rico. Yeah.
I thought I heard they are fixing it, but no. Okay.
It's all about money.
Yeah, right. Okay.
Right. They're proposing
Lots
lots of money. So they're proposing to fix it, but there is nothing certain at this point.
Okay. Yeah, but yes.
So Arecibo had a 305-meter dish. I think somebody who worked there once told me that it was something like a 75 dB gain.
Oh.
Whereas, DSS-14 only has a 70-meter dish.
Yeah. Magnitude different.
These both run in the, in the 2 gigahertz to 8 gigahertz range. Arecibo used to be down in the 400 megahertz range, but the more recent is 2 gigahertz. So Arecibo was 20 times more sensitive than to Goldstone. And, that's what we lost when Arecibo died. Not to mention that it had a heck of a transmitter on it. So just for scale, this is the Goldstone dish, DSS-14, and that little person at the bottom is my wife. And I assure you she's a normal-sized person. So that gives you a sense of scale here. The dish is 240 feet tall. It weighs 16 million pounds. The rotating portion of it alone weighs 8.4 million pounds, but it floats on a film of hydraulic oil that is 0.01 inches thick.
Woohoo.
So quite the engineering feat.
Must be under a bit of pressure.
Quite a bit of pressure, yes. So this is Arecibo. You can tell it's already falling apart in this photo. 1,000 feet wide. It had a 1 megawatt transmitter at 2.4 gigawatts. Being in Puerto Rico, it was away from a lot of radio frequency interference, but not all of it. The interesting thing about Arecibo is that it's a fixed dish. The dish does not tilt.
No.
Right? So what tilts, in some sense, is the detector and the emitter here at the top. It's on this track that can move back and forth. And it basically does an off-center feed of this, I don't know if it's parabolic or spherical, dish. So the way you change where you're looking on the sky is by changing the feed point.
Mm-hmm.
Okay, but you're very limited in how much of the sky that you can look at. Because, whereas, with Goldstone, you can point it anywhere. But with this, you can only point it within a fairly narrow angle. And I want you to remember back. I'm sorry?
Hard to move a dish that size.
It is hard to move a dish that size, exactly.
Yep.
So I want you to remember back to the fact that when you start going far away, you may go 3 or 4 light hours to get to one of the outer planets. Round trip time for radar is twice that. If we managed to do radar to Pluto, it would be 11 hours, right? But even going to like Mars, you're still a few hours. The Earth turns pretty fast, right? So if you fire radar at a point in the sky, you have to look at a totally different place for where it's coming back. And Arecibo did not have the ability to look very far off axis.
No, that'd make it tricky.
Right? So Arecibo was actually very limited in what regions, in what types of bodies it could do radar to, because it basically couldn't look at anything that was very far away because the Earth turns too fast.
I was just going to say that you can point Arecibo using the motion of the Earth, but you just said why that can't be done. It's too fast. It's
right.
You can't. Time is a problem. Yeah,
time is a problem. So you can do a thing called bistatic radar, where one dish is doing all the emitting, and then a different receiver somewhere totally different is doing all the receiving. And we'll talk a little bit more about that. But that does save you a lot of this problem. And in fact, they did it a lot with Arecibo, where they would like transmit with Arecibo and then receive at Goldstone or at Green Bank or at something like that. And that way, Arecibo didn't have to be looking in the right spot when the signal finally came back. Some other part of the Earth was then available to look at it. So basics of radar, you send a signal out, it bounces back. Okay. Things happen to the signal when they bounce off, though, and we'll be talking about those. Okay. But basically, there are a couple things. One of them is that you lose a lot of power, right? Normally, you think about transmission being 1/r², but the thing that you're hitting is, in a sense, also transmitting back to you. And it is losing 1/r². So the total loss on the signal is actually proportional to 1/r⁴, which is why you need a very, very strong transmitter and a very large receiver, because the signal that you get back is very, very small. So here's basically what happens. You send a signal up, it hits a body that is rotating. The nearer parts of the body reflect first, the further parts of the body reflect later. And all the signals that come back get Doppler shifted, depending on which part of this rotating body they hit. If the body is rotating towards the observer, then the frequency goes up. And if it's rotating away from the observer, the frequency goes down. So whereas you sent just a small pulse, what you get back is this diffuse thing that is spread out over time and it's spread out over frequency.
I see.
And that gives you lots of information about the thing that you're hitting the radar on, right? So I don't have to send just a pulse. I can send a continuous carrier. And in fact, I would really rather do that because, we're talking long distances, lots of loss, talk about QRM and QSB. If you send a signal out, the odds of you receiving that exact signal back, are pretty slim. So you want to have a lot of signal going out so that you have a chance of getting some of it back and so that you can integrate to get more signal to noise. Okay? But if you send just a continuous carrier out, how do you know which part of the carrier you're hearing when it comes back? Right? Maybe you're hearing this part, right? You have no way of measuring the range to the object. Okay, so what you do is you modulate the signal in one of various ways. So here you can do what's called binary phase code, where you change the phase of the signal using a pseudo-random code, just like they do with sped spectrum or GPS signals, for example. And it's a repeating code over time, but it doesn't repeat very often. And so when you finally get the signal reflected back, you can look at what the phase modulation is, compare that to the modulation that you gave it originally, and you say, oh, I know when I sent that exact signal out. It was at this precise time. And then that gives you the exact range to the object. You can also do the exact same thing just by doing frequency modulation, what's called a chirp. So you could just change the frequency over time. And then when you hear the signal coming back, you can look and see what the base frequency is and say, oh, I know what time I sent that frequency. So I know exactly how far away the object must be. So fundamentally, sending a continuous wave signal is useful for getting the Doppler shift, but it's not useful for knowing how far away the object is. Modulating it is useful for knowing how far away the object is. And once you've done both of those, gotten the Doppler shift and gotten the ranging, then you can start doing imaging. And this is the strangest image that you will ever see, and I will explain why in a moment. This is not a picture, and it is not showing you what you think it is showing you. So, and it just gets weirder. So let's think about what happens if I had a sphere up in space. This is an asteroid or something. It's rotating around this axis. So this side of it is coming at me, and this side of it over here on the right is going away from me.
Blue shifts.
Okay. So anything that comes back, any radio signal that comes back from this left side is going to be Doppler shifted up in frequency. And anything on this side is going to be Doppler shifted down in frequency. Right? And the further it is away from the center, the less the Doppler shift is, because the slower It's the other way around. The further away it is, the faster it's going to be rotating. And so the more the Doppler shift is. However, there's no way to tell the difference between this point and this point. They're both Doppler shifted by the same amount. Right? So I can't distinguish the north side of the object from the south side of the object when I'm looking at it with radar. They give me this, these data are layered on top of each other in the return signal. And I have no way of separating them. Okay, so there's this ambiguity that does not exist if you're looking at it flat on like a photograph. As a photograph, you can easily tell what the difference is between these two. But radar, there's no way to distinguish between the two. So these concentric circles, we're assuming we're looking at a sphere, these are different ranges, right? So this point, this circle is closest to us, and this circle is furthest away, you know, next further away, then further still, and then furthest still, right? So the circles represent the range, which is basically how long it takes the radio signal to come back to me. And the vertical lines are the Doppler shift. Because that's the different, and the lines should be curved a bit, but this is just a simple cartoon. Okay, but that's what we're plotting. We're not plotting an image. We're plotting range, and we're plotting amount of Doppler shift. So try to wrap your head around this for a second. The radar is coming in from the top in this image. That's pretty much the way these images are always drawn. Okay, as radar's coming in from the top, range is getting further away from us as you go down. Oops. Sorry. Yeah, come back. Okay, so the reason you can't see anything down here is because the radar can't see into the rock, right? This is shadow. This is radar shadow, okay? But what does it actually mean when you're going across horizontally? This is just the speed at which that particular point in the signal is being returned to us, how much the Doppler shift is, right? So this point right here, you know, is traveling fast, for example, but does that mean it's this fast, or does it mean it's this fast? Well, they're the same thing from the point of view of radar, right? This entire slice, this entire part of the circle is 1 pixel here. I can't distinguish between them. So this is not a 2D photo of the object by any stretch of the imagination. So here's a movie that may make this just a little bit clearer. On the left is what the radar is seeing, with the radar coming down from the top. And on the right is what a camera would be seeing if you were looking at the same object at the same time. Okay, so I'm going to stop it at a couple of key points here.
Rob, are these views from the same perspective?
Well, again, so on the right, so yes, they're both views of the same object at the same time from the same location. Wow. So in that sense, they're from the same perspective. I'm hesitating to use the word perspective because the concept of radar perspective and camera perspective are so different from each other, but you know, they're both on the same line of sight from the same observer.
Okay.
Okay. So the right is what you would see if you looked at it with your binoculars. Okay. I'm looking at the head, right? And the backside of it is mostly shadowed because I can't see through rock. Okay. But I can see the surface of the head fully. I can see its 2D glory, right? Every last little detail.
Yep.
Here's what the radar is seeing. This is the entire head. Right?
Right.
Okay. And so, and this is the shadow of the neck.
Right.
And then this is the backside of it, right? But this is not this, right? This is the merger of this half of this, you know, this half of this and this half of this.
That's because
Almost like image frequencies.
That's where it's bouncing off, right? That's why you're getting that, is where it's bouncing off the.
Yeah, it's where it's bouncing off, right?
Yeah.
And so let me give you a different perspective
It seems
here.
like it seems like an analog of image frequencies, right? Like in heterodynamic, the two directions in which it could be moving and both give you the same sense of the Doppler.
I don't think
maybe I'm
following.
overthinking it.
Yeah, I don't think I'm following that one. Yeah, I'm gonna stay away from analogies because this is hard enough to understand just by itself.
Thank you.
I mean, honestly, I have trouble wrapping my head around this, and I've been staring at this stuff for weeks now. You the people who it is so tempting to think of this as an image, and it just so is not an image. And I will give you an example in a minute of just how much not an image this is. I will show you an image that will just blow your mind. Not an image, sorry. So anyway, here's an example of what radar can see versus what an actual spacecraft can see. And you can see the radar is pretty good resolution, right? We actually get a 15 meter per pixel resolution on an asteroid. And this is Itokawa, which was visited by the Japanese spacecraft Hayabusa. And so this is a pre-mission radar image, and then you use that to make a model of what the gravity is going to be like in the shape, and you send the spacecraft there, and you sort of know what to expect. But then here's an actual photo. And so radar is pretty good,
Amazing.
right? And then if you take a lot of these radar images as the asteroid is rotating, you can build up a 3D model, right? And then you actually do get an image, but it's one that's been mathematically derived by taking multiple radar slices. And this is, for example, a 3D image taken from multiple radar observations this is the asteroid Bennu, visited recently by the OSIRIS-REx spacecraft. And you can see it's pretty good. I mean, here's this little boulder down here, and here's this little boulder here, right? So, this is pretty far away. And these were all done, I think, with Arecibo, sadly. But, radar is really pretty impressive in what it can accomplish. And of course, the other thing that you care about is whether or not any of these bodies are going to hit the Earth at some point, right?
Of course.
So there are all of these things that are called near-Earth asteroids that are on orbits that are relatively near the Earth at some point in their orbit, and that could conceivably impact the Earth at some point in the future. So these are really hard to see using visual light telescopes, but they're not bad to detect using radar. And radar has an incredible precision in terms of where they are on the sky. And so you can get very precise orbits for the asteroids by using multiple radar observations, sometimes as much as 1,000 times better than you would get quality of orbit from purely visual observations. So you can tell here that basically starting back, in the early Arecibo days, this is the cumulative number of asteroids that have been analyzed, right? There have been so far 991 near-Earth asteroids as of this March, just a month and a half ago.
Yeah,
so this is a big deal because we want to know if something's going to hit the Earth or not. And many of you may remember the Chelyabinsk meteor that hit in 2013 over Russia.
Yeah.
And if you're not familiar, I suggest you look it up on YouTube.
Yeah.
There are lots of wonderful videos of it because it turns out that in Russia, everyone has a dash cam in their car because you can't trust the police and you can't trust the people that you have an accident with.
True.
So you record everything. And so everybody managed to film this meteor coming through the sky on their car's dash cams. And it actually provided a lot of scientific data for people to analyze. And one of the researchers at SETI, Peter Yuniskins, is famous for traveling the world finding the remnants of these meteors that have been seen and searching, weeks at a time, basically doing search and rescue grids to find parts of these meteors. And he actually found part of the Chelyabinsk meteor, I believe. But one of the things that was interesting about it is that no one was actually injured by the meteor itself, but there were 1,500 people, plus or minus, who ended up getting injuries that required medical attention from the shockwave. And it's not that the shockwave itself was dangerous.
Wow.
It's that everybody said, oh, look, there's a bright light in the sky. I think I'll stand in front of my large plate glass window and see what it is.
Yeah.
And the glass broke and cut them. And I was actually looking at this earlier today. There's some really interesting YouTube videos that are compendiums from security cameras all over Chelyabinsk of what happened when the shockwave hit. And it's fascinating. You should go look it up. I mean, some of them are, these giant loading doors from like a warehouse just get blown in, or an apartment complex has all of its windows blown out, or, people get blown down walking down the street. It's really interesting to watch. And that was a small meteor, right?
Did anybody detect that meteor before it even came? Did anyone detect that meteor? Did we know about that meteor before?
No,
Okay.
we did not know about it. It was relatively small, and we only know about a fraction of the meteors of the asteroids that are out there. And this is one of the reasons that, basically we need funding and we need equipment to look, because doing sky surveys like this is hard. right? You're looking for tiny objects in a very vast sky. And every now and then one of them can be dangerous, right? And so I'm sure you've all heard of Apophis, which has been in the news on and off for the last decade or so. This is my favorite headline of all time that says that the asteroid will hit us twice. I'm really kind of wondering. I'm really kind of wondering how it's going to survive after the first one. But this news article even came complete with a simulation about the ring of fire that was going to happen when Apophis hit the Earth.
Is that the first time or the second time?
I don't know. And this was just November of 2019. I mean, this was just a year and a half ago, or 2 years ago. But anyway, here's where radar comes to the rescue, where the Green Bank telescope was able to do radar observations of Apophis, and they were able to fine tune the orbit much better than they were able to do with previous optical measurements. And they could say categorically that there would be no Earth impact of Apophis in the next 100 years or more. And this was just in March, right? This is just 2 months ago. So, radar to the rescue. And we finally know just 2 months ago that we're not going to die from Apophis in the next 100 years. And this is a big asteroid, 1,100 feet wide. I mean, this is enormous compared to Chelyabinsk.
Bigger than a school bus, then.
Bigger than a school bus, yes. All right, so, but there is scientific stuff that happens with this radar as well for the asteroids. And one of the most interesting things, I think, is that there are all of these binary asteroids that we didn't know about, where there are actually basically an asteroid and then a smaller asteroid that are orbiting each other. So it's sort of like an asteroid and its moon. There are also trinary asteroids out there, but 1 in 6 asteroids is binary. And I don't think that anybody would have predicted that originally. Out of those 1 in 6, 14% of them are what are called contact binaries, where they are so close together that they are not rigidly connected. This is not a, like solid rock that's holding them together. They're being held together by their own gravitational attraction, and they're basically orbiting around a center point, but they're so close together that, these are basically big piles of dirt that they are touching. And they're basically, binary bodies that are orbiting so close that they're touching each other. And these are incredibly common. 14% of all of the contact of all of the binary asteroids are contact binaries.
Question on that. A question: Are there any instances found of 3 or more?
Well, there are definitely 3 or more that orbit like this. In fact, there's a researcher at SETI, Frank Marquise, who specializes in studying what I would call the trinary asteroids. I don't know that there are any contact trinaries. That might be kind of hard to manage, but there are plenty of the trinary, just plain asteroids like this.
Imagine the impact image from something like that. It'd be like cluster shot.
Yep, right. And again, remember, these are not images, right? These are delayed Doppler images. So these are all in that strange coordinate system that we're talking about. So I know your eye will look at this and say, oh, look, an image, but not an image.
So is the pixel density of, say, 4405 pan a newer radar, which is why it's more refined and finer pixels than 11066 happens to be?
I don't know. I think these were all taken with Arecibo, if I remember correctly. And it could be just distance. Or it could be that the atmosphere was noisy that day. I honestly don't know.
Okay.
So the last thing that I wanted to mention with the radar is that we have looked at planets with the radar and have learned some really interesting things. So Mercury, as you're probably well aware, is very close to the sun, and as a result is very bright. You can only see it early in the morning, late at night, and it's always very bright. So if you look at it with a telescope, you basically see a big white dot. You don't see surface features like you do on Mars, for example, because it's just too bright. So for the longest time, people had no idea what the rotation rate of Mercury was, how long its day was, basically, because they couldn't see it rotate, because they couldn't see its surface. It was too bright in the sun's glare. So normally you would think that a planet that is that close to the sun is what's called tidally locked. So our moon is tidally locked to the Earth. That means that it rotates once on its axis in the same time that it orbits once around the Earth. And this is why we always see the same side of the moon, right? It takes 28 days to rotate on its axis, and it takes 28 days to go around the Earth, so it's always pointing at us. Any binary system that is sufficiently close will eventually become tidally locked, because the tides that we've been talking about end up changing the rotation rate of the two bodies until they're in sync. Yeah. It forces them to be in sync eventually. So people would have thought that the Mercury was probably tidally locked with the sun because it's so close. Radar was able to measure using Doppler shift its rotation rate. And it turned out that Mercury rotates on its own axis every 59 Earth days and orbits once around the sun every 88 Earth days. Now, this is a 3-to-2 ratio. And the 3-to-2 ratio ends up being a stable configuration. It's not tidally locked 1-to-1, but it turns out that 3-to-2 ends up being a stable resonance. So Mercury has this very weird thing where it rotates 3 times for every 2 orbits around the sun. And sometimes Mercury is very close to the sun, and sometimes Mercury is a bit further from the sun. And so there are times that the sun is moving quickly in the sky and times it's moving slowly in the sky. There are times in Mercury's orbit where the sun rises twice on the same Mercury day. It rises a bit, and then the sun goes back down below the horizon again, and then it rises a second time. And again, there's some great YouTube videos of this, of people who've done simulations where you can watch what a Mercury day looks like. And it's pretty freaky. But this is something we didn't know without radar. We also learned that Mercury has a partially molten core. We found these radar bright materials that were in shadowed craters, which are presumably water ice. Mercury may be close to the sun, but that doesn't mean that parts of it aren't really cold if they're deep in craters that don't get any sunlight, because there's no atmosphere to carry the heat around. We did the same thing with Venus. You know, Venus has this incredibly dense atmosphere, sort of like Titan does, except Venus is even nastier with, with sulfuric acid and things like that. And so we didn't know how fast the surface of Venus rotated on its axis. I had no idea, because all we could see was the atmosphere, and the atmosphere is pretty bland looking, right? But the bottom is a delayed Doppler image of the surface of Venus. That was done by the 100-meter dish at Green Bank. And it turns out that Venus orbits the sun in 224 Earth days and rotates on its axis in 243 days backwards.
What?
So it is the only major body in the solar system that rotates on its own axis the wrong way. Because everything in the solar system was formed from the same rotating disk of dust and interstellar atoms and molecules. Everything ends up, by conservation of angular momentum, everything ends up orbiting and rotating the same way. So Earth, looking down from the north on the North Pole, it rotates counterclockwise. It orbits around the sun counterclockwise. The sun itself rotates counterclockwise. All the other planets orbit around the sun counterclockwise. Venus rotates the opposite direction.
How did that happen?
They think it's because it got hit by something really hard and flipped over.
I'm thinking too. And flipped its orbit, yeah.
Yeah, so the orbit is normal, but the direction of rotation on its axis is backwards.
Wow.
And Uranus, by the way, is on its side. We're actually looking at its North Pole from Earth. So we're not looking at the equator like we are all the other planets. So something hit it also and flipped it, but only 90 degrees. Venus got flipped almost 180 degrees.
A question about Venus. Are those two numbers an exact integral ratio or only approximate?
No, the Venus is, as far as I know, is totally random. Venus is far enough away from the sun that you wouldn't expect it to be tidally locked in the age of the solar system. Just like we don't expect the Earth to be tidally locked to the sun at this point. That would be really unfortunate for us if it were. One very hot side of the planet and one very cold side of the planet. So I don't think there's any reason to believe that Venus has an integer ratio of any kind. It's just random.
Did you say that the Uranus, the North Pole, is always pointing to the sun? Is that?
You're always looking at you're always looking 90 degrees off from the equatorial plane. Let me put it that way. So sometimes you're looking at the North Pole, sometimes you're looking at the South Pole, sometimes you're looking at the side.
Right.
Right.
Okay.
Right. But you're not looking
Because
at
it would be funny if that was. Yeah, it'd be funny if that was tidally locked to the sun.
Yeah. No, that would be pretty. That would be pretty bizarre.
Yeah.
No, that would not be.
Yeah.
That would be pretty strange. All right. So here's our last picture, and the one I want you to try to wrap your heads around. This is a radar image of Saturn's rings, and they cross each other.
Yeah, they do.
This is my point about it not being a photograph and how delay Doppler is a totally different animal. So let's try to figure out what's going on here. So we're seeing the A ring and the B ring. Okay, I'm not even gonna tell you which is which at this point. Okay, but we're seeing the A ring and the B ring somewhere because those are the two main dense rings. Okay, now remember that what we're seeing here vertically is range. So this is pretty easy to understand. This is distance to Earth. This is what you would expect it to be.
Yeah.
Okay.
Yeah, far, near, and far, near, and far.
Horizontal is amount of Doppler shift. Now, if I have a solid body, like an asteroid or a moon or something like that, then there is a constant change in Doppler shift as you go away from the center, right? You know, the amount of the things are moving slower close to the center, and then they're moving faster further from the center.
Right.
Right? That's because it's a rigid body. And if basically you have a lever arm, right? If you take a line of particles coming from the center of the body out toward the surface, you know, the ones that are close to the center have a very small lever, and the ones that are farther away have a very large lever. And when you swing a large lever, you know, it goes faster, right? That's why you hit things at the ends of bats, right? Because they have more velocity. But the rings are not a uniform rigid body. And this is why I was emphasizing that earlier. Every ring particle is on its own orbit, and things that are closer to the gravity well orbit faster, and things that are further from the gravity well orbit slower. This is the opposite of what happens for a rigid body. Okay, so ring particles that are closer to the planet are actually orbiting with higher velocity than ones that are further away. So if I am looking down here at the bottom, I am looking at everything basically on edge. There's very little Doppler shift here, right? Because something that I'm looking at as it's going right to left is a lot less Doppler shift than if it's coming directly at me. Right. So here, this is all more or less constant Doppler shift. I mean, it's a little bit different, but it's not a lot different. Yeah. But the range is very valid. Okay. So this is actually the closest you're going to see to an actual image here, which is the A rings on the outside, the B rings on the inside. The range is true. The Doppler shift is, you know, not varying very much. But because you're looking at it edge on. But here, the B ring, which is the one that's closer to Saturn, is orbiting faster. And so it has higher Doppler shift, both towards and away from the observer. Whereas the A ring, which you're now looking directly at, is coming towards you or away from you, is orbiting slower, and so it has less Doppler shift. Okay, so here, this is not range anymore, right? Don't think of this axis as distance. This is speed, right? That's part of the problem, is that this is distance and this is speed. They're totally different units on the two axes. So this is now the B ring, which is the inner ring, but it goes faster. And this is now the A ring, which is the outer ring, but it goes slower. We can look at that as this contour plot, where basically these dashed horizontal lines are lines of constant range. And these curved dashed lines are lines of constant Doppler shift. So you can see as you're looking here, like here's a ring particle coming directly at me, right? And you can see it's coming at me pretty fast. And a ring particle that's closer to the planet, but here would look the same Doppler to me, okay? But there are no ring particles anywhere over here that have that level of Doppler shift because nothing's coming at me, right? So what you end up with is a point where the lines of Doppler shift and the lines of range are parallel to each other. And those are the points where you get basically what look like a big clump of ring particles, because you can't distinguish whether they're going faster or slower because they're all at the same Doppler shift. See how these are all parallel here?
Yeah.
And that's what these bright spots are. So here, you don't see much Doppler, but you do see range. Here you see a lot of Doppler. And you're almost looking at two different types of images in these two regions. And then here, there's ambiguity. You don't know what you're seeing because all the Doppler is the same. Clear as mud?
Yes, absolutely.
Got it.
All right, so I'm going to leave you with this beautiful photo, and that is the end of my presentation. I'm happy to take any more questions.
I have a question
Mm-hmm.
about the occultation part of the presentation. What was receiving the signals passing through the rings when Cassini was sending them?
You mean in the occultation ones we were talking about earlier?
Yeah.
The Cassini is received by the Deep Space Network. So that's Goldstone in Southern California, Canberra in Australia, and I always forget the one that's in Spain. But there are 3 deep space networks around the globe so that there's always continuous coverage of the sky. So one of those big dishes was receiving the signal. I don't know which one.
Oh, okay.
Those were originally set up during Apollo so that we'd always have communication with the astronauts.
There was a story just recently that NASA has funded research into building an Arecibo-like telescope on the backside of the moon using a
What?
crater.
Well, they've been talking about that for decades. I don't
for
know.
a long time. Well,
Yeah.
they've only put 500 million up to research how to build the thing.
Okay.
So would the development and or implementation of that telescope, obviously decades from now, have impact on how you do your research now?
The main thing that a telescope like that would be used for is probably receiving incredibly faint signals.
Yeah.
Right. So that's going to be used for measuring, for receiving things that are being sent from the cores of faraway galaxies, things like that. You don't really need something that big and that radio quiet to receive planetary radar, right? You can build that here on Earth for 1% of the cost and a lot, and a lot less effort. And you certainly can't do radar from a site like that because you're not going to have the power source on the moon to generate the transmission, right? So it's going to be receive only. So generally speaking, a big dish like that on the far side of the moon is specifically for receiving incredibly quiet, in an incredibly quiet environment, very, very low energy signals from very far away.
That side of the moon would never see the sun, right? Is that why they would do it?
No, so remember there's a very big difference between the dark side of the moon and the far side of the moon.
Oh.
So the Pink Floyd notwithstanding, there is no dark, there is no dark side of the moon.
There's no dark side of the moon, right?
There is no dark side of the moon. The moon, because it orbits around the Earth, once per month, always has some half of it illuminated by the sun. And when we see a new moon, that just means that the other side that the far side of the moon is full from the point of view of someone on the other side, right?
Oh, so
But
Pink Floyd-
what it
Floyd was
is-
correct. Okay.
Yeah, what it is though is it's in the shadow of the Earth's noise.
Right.
Exactly.
Right.
Within radio, it's in radio shadow.
Yeah.
And if you guys haven't seen, the Chinese did an amazing job of sending a rover to the far side of the moon. And it's been there for like 2 years now, right? It's been there for an incredibly long time, investigating the far side of the moon and sending back some really spectacular photos. And the problem with having a rover on the far side of the moon is a radio problem, which is that you can't communicate with the Earth, right? And so they actually did something very, very clever, which is that they put a relay satellite in orbiting a Lagrangian point that is always visible from both the far side of the moon and from the Earth at all times.
That's just geometry. But
Yeah, it's geometry and some really cool gravity.
oh yeah. All right.
All right. Well, I know this was incredibly long. I think we managed to go almost 2 hours here, but I hope it was interesting and I hope it was worth it for you.
Very
Absolutely.
interesting. Thank you.
Absolutely, Rob.
Thank you.
Let's give him a hand, guys.
Yes.